Okay, class, where we are, we're still in respiratory. I now have pulled up my Respiratory 2 PowerPoint. My Respiratory 2 PowerPoint. So that's where we are now. Okay, in this particular PowerPoint, we'll look at internal, external respiration, oxygen carrying in the blood, hypoxia conditions, hyperoxia a little bit, carbon dioxide carrying the blood, respiratory control, acid-base control in the body, and a few, just a selected few, respiratory diseases. So that's what we'll look at in this particular one. Okay, let's get started here and see where we go with this. All right, external versus internal. External respiration basically is when you are bringing air in and out of the lungs. Internal respiration is when you're exchanging oxygen and CO2 inside the body with the tissue cells. So lung part external, tissue cells internal. Okay, and that's what this particular slide showed. All right, so now we go to this slide here, which we'll go to there, and we're looking at picking up oxygen. So the oxygen, see, now we get back into Dalton's law of partial pressures. Go back, review that. Dalton's law of partial pressures, because we're looking at putting oxygen in the bloodstream, and it's going from a high partial pressure to a low diffusion, and CO2 high to low also. So that's what we're looking at here. So this is an overview you can glance at. All right, now I go to my numbers. I go to my numbers. So this is what I want you to know. All right. Let's start here, and matter of fact, I can correlate it with over here. All right, the P here, this is the real symbology used in respiratory and science and so forth. The P stands for partial pressure. We don't do a PP, we just do P. The PATM means the partial pressure of atmospheric gas, whatever that gas is. Just for example, like the partial pressure of atmospheric O2. The P big A, capital A, is the partial pressure of alveolar gas. The P little a, which is the one that you really will see on respiratory reports, is the partial pressure of arterial gas. The P little v is the partial pressure of venous gas. Okay? So let's go. This is the calculation. We would have done it in the last PowerPoint series. But anyway, the PATM is 160. Okay, how did we get that? 21% times 760. 760 is atmospheric pressure. PaO2, about 104. That's the alveolar gas. Okay, see right here, here's alveolar. Let's look over here, and you see that 104. Okay. Pa little aO2 is the arterial. Okay, so we're coming in here, this is the lungs, but we're coming out here, okay, with arterial. See, right there, they got a 104, I'm putting about a 102, and I'll explain why mine's a little bit different, but it's around that range. 102 to 103 I have. PVO2 is 40, okay. The PVO2 would be this right here. That's what's going into the lungs. So just kind of study this. You have to follow along. Then if I go to CO2, carbon dioxide, the PATM is about a 0.3, okay, millimeters. The PaCO2, which would be alveolar, is about 40. Okay, see, it's not much in the atmosphere. That's alveolar. The P arterial CO2, okay, which would be this here, that's arterial side, about a 40. And the PVCO2, which is the venous side, coming into the lungs, that'd be about a 45. So you see, you can correlate, take your time now, and correlate these numbers that I've calculated. All right. So then we go a little further here. Now, I'm going to go here now, though. Before I do that, I'm going to go to this over here. All right. Now, this comes from another book. This comes actually from a respiratory book. I'm going to slide over a little bit. All right. Let's look here what we have here. All right. This is the way I want you to look at it. Now, in the atmosphere, you have nitrogen. Remember, that was 79%, so that's quite a bit. Nitrogen is the largest in the atmosphere. O2, CO2, and then remember the dew point humidity level. The dew point humidity level. The dew point humidity level is the amount of atmospheric water. The amount of atmospheric water. Okay, so here we go. Here would be, this would be in the atmosphere. Okay. This would be when you breathe it in through the mouth or the nose. We already talked about that. Now, what's the job of the nose? Warm, filter, and humidify the air. Moisten the air. All right, the total here can only be 100%. It's 100%. That 760 is the total. So we percentaged out that. That was Dalton's law now. Law of partial pressures. Okay. When we bring the air into the nose and mouth, we still got to stay at 100%. But when we get into our air passages, bring it in, we increase the water amount. There's more humidity in your mouth and nose than it is in the atmosphere. I think it doesn't take a great genius to know that. So then, if we up this, increase this of the 100%, the others are going to come down some. So we went from nitrogen to this in humidified air to this. We brought this up. Now look, we brought the oxygen down coming in. Now we haven't used any oxygen. We just brought it in through the nose and mouth, right? But the reason the value went down in the humidified air is because what? The water vapor went up, and you can only go to 100%. All right. Now we're bringing it down into the alveoli. So I'm going to come over here. We're bringing it now into the alveoli. All right, when we bring it into the alveoli, now this is what I want you to notice. Let's look at the CO2. See, the CO2 amount went up. Why? Because you're putting CO2 into the alveoli. Coming from what? The right ventricle pulmonary artery. Remember, artery has deoxygenated blood because an artery is a vessel that leaves the heart. It's not a physiologic term, it's an anatomy term. Go back and review that. So this CO2 is coming in. So the CO2 amount has gone up, which means you're going to squeeze out some. Now the water vapor is the same, but this went up. So these two kind of squeezed down some, particularly this one, 104. See, that brought that 104 there. Okay. Now, the expired air, let's look at that. 120. Whoa, where did that come from? How could you, because your body does make CO2 to exhale, right? Your body does exhale CO2 primarily. Why then is it 120 here? Because some of the air that went into the alveolus, or some of the air you breathed in, we're going back to tidal volume. Some of the air that you breathed in did not get exchanged. Some of the air, what you breathed in, did not get exchanged because it was in the anatomic dead space. Go back, review that. The anatomic dead space was from the nose and mouth all the way to the end of the terminal bronchiole. That air stayed at 149 because it never got exchanged. That oxygen stayed there. It never got exchanged. Okay? So the alveolar amount did. Okay, so now let's break this down. If I brought in 500 cc's if I brought in 500 cc's of air, right, and 350 got exchanged, they were 104. But 150 did not get exchanged. That was the anatomic, and that stayed at 149. So then when you breathe out, what are you going to breathe out? You're going to breathe out the upper stuff first, which would be that didn't get exchanged because that's in the conduit. Then you'll breathe out this. So the value then, if we just eyeball it, the value is got to be above 104. But it can't be 149 because 149 is that. Now, if somebody wanted to calculate that, all they would do is to take the 150 times this, but as a percentage. So you'd have to do 150 over 500 and 350 over 500. Get that percentage. And it would be no more than a weighted average formula. And if you did that, and if you question, if you email me something and say, how do you do that? Then it would come to about this right here, 120. So that's why the exhaled air has more oxygen, even though you don't make the oxygen in the body to be exhaled. So that's what this is, okay? All right. Let's go a little further. So we did this here. We talked about that. Now we looked at the composition of alveolar gas. The atmosphere is mainly nitrogen. But nitrogen has a poor solubility coefficient. Now I want to hit this for a moment. We really are not going to talk about nitrogen much, but I want to bring this up right here in this one. Nitrogen has a poor solubility coefficient. Water does not like it. Water does not like it. Okay. Now, how do you get nitrogen in the blood? Okay. Hemoglobin doesn't carry nitrogen, so it doesn't like it when we get into it. The water in the blood doesn't like it. But there is a little nitrogen in the blood. There is a little nitrogen in the blood. Okay. Now, how then do you drive more nitrogen in the blood? Increase the atmospheres. What did I just say? Increase the atmospheres. See, we're back to Henry's law. What does Henry's law say? The amount of gas that will dissolve in a liquid is based upon the partial pressure of the gas above the liquid and the solubility coefficient of that gas for the liquid. We cannot change the solubility. That's set in chemistry. But we could change the partial pressure. So if all of a sudden you were in a scuba tank, a atmospheric air, just regular atmospheric air, room air, scuba tank, and the scuba tank would have a high pressure, that it could drive that nitrogen into the blood. Nitrogen didn't want to be there. It'll drive it into the fluids. So then, as you go down, you'd have the scuba tank plus the pressure of the water, what we call hydrostatic pressure. Okay? So then as you go down, if I'm not mistaken, every 33 feet of water that you go down underwater, that's another atmosphere. So let's say you go 100 feet. That's 3 atmospheres. That's 3 times 760, which would mean nitrogen then would be driven into the blood and into the tissues too. So now what you need to do is ascend slowly, because you want the nitrogen that came in to go out through your lungs, to be blown back into the scuba gear. But if you come up too fast, the nitrogen says to heck with it, and it just starts coming out. It'll come out under the skin, in your muscles, under the skin, any place, and start causing cramps. It'll also come out in the brain and cause nitrogen narcosis, and you'll pass out. The cramps are what we call the bends. So that's the reason you have to come up slow. One last thing. Those that can pop their fingers, pop their knuckles, that's nitrogen. Those that have a laxity, when they pull on it, it allows those nitrogen bubbles in the synovial fluid to come out. So that's all I'm going to say on nitrogen. Even though it's high in the atmosphere, it's not that much in your fluids because of a poor solubility coefficient. Thank you.